Okay, so now the recording is ongoing. How they react with optically active reagents. Now, in chemistry, whenever we talk about reaction, you see a reactant getting in contact with what? A reagent. And then the reagent could be maybe an oxidizing reagent or a reducing reagent or what have you, to change the reactant into a product. Okay. Now, for reagents that are not optically active, these enantiomers would as well react with them equally. There wouldn't be any difference. But those that are optically active, then that is where these enantiomers will also react differently. So somebody will ask, what is an optically active reagent? We have already explained that when we talk about an optically active compound, it means that compound, one, has a chiral center, and two, that compound has no plane of symmetry. So the compound has a chiral center, it has no plane of symmetry or line of symmetry, then we say that the compound is optically active. So if a reagent also meets these two criteria, then that reagent is what? Optically active. And this optically active reagent react differently with a pair of enantiomers. They react differently with a pair of enantiomers. So these are the two distinct ways that we can see a difference between enantiomers. Of course, enantiomers have equal and opposite rotation. They have equal and opposite rotation. So take note of that. So if you take the one on the screen like this, whilst the one on the left, you see that the angle of rotation is indicated by plus. The one on the right is what? Minus. Okay. And of course, when they rotate by the plus, which is the clockwise rotation, it is called dextrorotatory. And if they rotate by the minus sign, which is the anti-clockwise or the counterclockwise rotation, we call that one the level rotatory. But then take note that all other physical properties are the same. And here I've given you examples. Density, if you compare the density of two enantiomers, they are the same. Boiling point, if you compare, they are the same. Identical. If you compare melting point, solubility, and other physical properties, you see they are similar or identical. Now, configuration. Okay, and then we're going to look at two types of configuration, which we call the absolute configuration. And the two types of absolute configuration, we have the R and then the S. Those of you who remember our first lecture, and then I was talking about the lemonin and then the epinephrine drug, we said that one of them, the R was okay, but then the S was toxic. And then when we come to maybe the lemonin, we said that the R form gives orange its what? Odor or flavor, while the S gives lemon its odor or flavor. So this R and S, what do they mean? What are they? And here we talk about what? Configuration. And the two types are the R and S. So we will be looking at how to determine the R and then the S configurations around a chiral center, and then that should be incorporated to the naming system of organic compounds. So that if you are giving a compound which is optically active and exists in two forms, which are mirror images, and of course, non-superimposable, and we call them enantiomers. When you are asked to give the IUPAC name of this pair of enantiomers, one of them, you probably will have to begin with what? R. The other one, you have to begin with what? S. But then how do you know which one is the R and which one is the S? So configuration is simply the three-dimensional arrangement of the groups attached to an atom in space. And when we talk about stereoisomers, all they really represent is that they differ in the configuration at one or more of their atoms or chiral centers. The RS system is a sequence rule for designating the configuration of chiral carbon atoms. So anytime you are able to identify a chiral carbon, a chiral center, a stereogenic center, then around that center, you should be able to indicate the configuration there, whether it is R or it is what? S. Now, R here, full meaning is rectus. Rectus. And rectus implies clockwise direction. Then the S here means sinister. Sinister. And sinister used here means anti-clockwise direction. So that is for your notice. So the configuration relates to the three-dimensional sense of attachment for groups attached to a chiral atom or group of atoms. So let's look at what is on your screen. You see that there's a central atom labeled C, that is carbon, yellow, okay? Then it's bonded to 1, it's bonded to 2, it's bonded to 3, it's bonded to 4. Now, these groups labeled 1, 2, 3, 4 are groups that are attached to the chiral center. And of course, for the C to be a chiral center, it means that the numbers labeled 1, 2, 3, 4 should all be different. They should be different. They should be different. None of them should be the same. Meaning, this 1 cannot repeat itself as 1 here. 2 cannot repeat itself. 3 cannot repeat itself. 4 cannot repeat itself. They should all be distinct. That's why you have 1, 2, 3, 4. As soon as you see 1 appearing twice, then it means that this carbon is not chiral. 2 appearing twice, it means that it's not chiral. The same thing applies to the others. So for now, we see this carbon as chiral because the numbers here are all different. So it then qualifies the carbon to be a chiral carbon, a chiral center. Now, how do we arrange these groups in space? Can be done, okay, in such a way that when you move from 1 to 2 to 3 to 4, the direction of movement follows a clockwise direction. Follows a clockwise direction. And the clockwise direction is what we call rectus in Greek, meaning clockwise, right direction. And that is denoted by the letter R. The same way, you could also have these numbers 1, 2, 3, 4 arranged so that you can move from 1 to 4 and the direction of movement will be anti-clockwise or counterclockwise. And that is called a sinister, S. S. Now, between these two, can somebody tell me what they think? You could see that, look at where 2 is here and 2 is here. It's showing some mirroring. Where 1 and 1 is, it's also showing some kind of mirror relationship. 4, 4, 3, 3. So it means that between these two compounds, they are showing that kind of mirror image relationship that is known to what? Enantiomers. But then, of course, if you try to superimpose one on the other, you realize that these two will come and sit on 1, 1 will come and sit on 2. 4 will sit on 4, 3 will sit on 3. So at least 2 of the numbers will fit well, but the other 2 will not fit well. And that means that they are non-superimposable. And that qualifies them as what? A pair of what? Enantiomers. So anytime we talk about a pair of enantiomers, it means you are referring to what? 2 compounds. Okay. If you say there are 5 pair of enantiomers, 5 pair of enantiomers translates to what? 10 compounds, because each pair involves 2. So if there are 5 pairs, then that means what? 10 compounds. And if there are what? 20 pairs, you are referring to what? 40 compounds. Any question, please? Any question? All right. It means you are really following and then understanding. So we can move on. So the R and S are from the Latin words rectus and sinister. R configuration, which is the clockwise, means rectus. So wherever you see the Latin word rectus, it means right direction, right hand direction, clockwise direction. Whereas the S configuration is the counterclockwise or the anti-clockwise, which is the left hand direction. So now we want to know, why do we start from 1 and move to 4? Okay. Now, when you're able to identify the 4 groups around a chiral carbon, we normally will use what we call the Can-Ingold-Prelog convention to then assign an order of priority sequence using their molecular weight. If you remember, in our introduction to organic chemistry, when we go to the geometric isomerism after the cis and trans, and we said that when we are confronted with complex alkenes where we cannot use the cis and trans, what we do is that we look at the 2 groups that are bonded to the carbon with a double bond, and in terms of their molecular weight, assign an order of priority sequence. The heavier one is giving 1, then the lighter one is giving the number 2. Then you go to the other carbon and you apply the same rule. Then when you are finished, when 1 are on the same side, we call it Zusammen, Z. And when the 1 are on the opposite direction, we call it what? Antigen, that is E. So the same convention is what we are going to use here to assign these R configurations. Please just give me a minute. I'll join you pretty soon. All right, I'm back. So we are going to apply the same Kern-Ingold Prelog conversion in helping us to be able to, first of all, assign an order of priority sequence. And then when we are done, then we assign at the highest priority point and move to the least priority point. And the direction of movement, if it is clockwise, then we have the rectus R configuration. If it is counterclockwise, then we have the S configuration. So first, the rule is the same priority rules we developed for the EZ stereoisomers. Like I said, higher atomic number has higher priority. And if priority cannot be decided based on the first atom attached, we then move to the next atom. We follow the same pathway unless we are able to separate them. And then where we have multiple bonds, like double bond, triple bond, you have to expand them by replicating the atoms attached to each other of the atom, of the bond. And that's what we call the Kern-Ingold Prelog. We are already conversant with this rule. And so we are going to apply the same rule at this point. So now let's look at bromochlorofluoroidomethane, which is one of the compounds that we've come in contact with as far as we started this course. So now, first of all, you identify a central atom carbon here, and you realize that there are 4 different groups: iodine, bromine, chlorine, and fluorine. Then, in applying the Kern-Ingold Prelog conversion by way of molecular weight, which of these group has the highest molecular weight? Iodine is 127, bromine is 80, chlorine is 35.5, iodine is 19. So definitely, fluorine is 19. So definitely iodine, which is 127, is the group with the highest weight. So that is giving the highest priority. And the highest priority, we want to denote that one by the number 1. Denote that one by the number 1. Then bromine is next, 80. So 2. Chlorine, 35.5, 3. And then fluorine, which is 19, 4. So after using the Kern-Ingold Prelog conversion to assign this priority sequence, then stand at the highest priority group, which is iodine, and move to the second, the third, and then the 4th group. Now in the movement, you see that you are moving in a particular what? Direction. And this one follows what? A clockwise direction. Clockwise direction. And so we say it's what? Rectus. So the configuration around this chiral carbon here is R. Is R. Now, when you come to this side, when you start from 1 and you move to 2 and you move to 3, the direction is what? Counterclockwise, anti-clockwise, and that is sinister, S. There's a question probably some of you want to ask. I don't know whether you have seen it. If not, I'll ask my own question and then give you an answer. I hope any one of you is not saying that, say, but this one, from 1, we got to fluorine, 4, before coming to 2 and 3. Is any one of you thinking like that way?
Yeah.
Yes, sir.
Very good. So now the explanation is that in stereochemistry, okay, whenever you pick a point, which you are referring to as what? Chiral, whether it's a carbon or a center, the other 4 groups that we say surround the carbon, which we are calling it chiral, at no point in time can you see the 4 groups. So have that one in mind. Okay. Assuming this lecture was face-to-face, and then I was in the lecture hall with you, I would have brought in my molecular model. Now the molecular model, there I would have shown you the central carbon and then put the 4 groups on it. And then when I give it to you, and from your eye level, when you view it, you can only see 3 of the 4 groups at a time. Okay? You can only see 3 at a time. And so, in the molecular structure drawn on the screen, you see that the iodine is on a solid line, solid bond, isn't it? Chlorine is on a solid bond. The bromine is on a flying wedge. And then the fluorine is on a broken line. Let me give you the interpretation of this type of bond. What it tells you is that even though on the screen we can see all the 4 groups, but in reality, one of them cannot be seen. One of them is hidden. So when a group is on a solid line, like the iodine, like the chlorine, it means it is in the plane. And if any group is in the plane, automatically you will see that group. So it means we can see iodine, we can see chlorine. Now, when a group is on a flying wedge, the interpretation here is that a flying wedge object means that the group is pointing towards you. So any group that is pointing towards you, the viewer, it means you automatically will see it. Then, when we see the broken line, okay, this broken line, what it means is that it's an imaginary line. It's not something that is real. You cannot see it. Even though on the screen, you can see the broken line and you can see the fluorine, in reality, the meaning of the broken line means that this fluorine, this particular group, is hidden behind this carbon and that you cannot see it. That is what it means. So, if you are to view it from the least group, that is the fluorine, and you are moving from 1 and you are coming to 2, because we know the meaning of this broken line means that the fluorine here is not real, it's not physical. So we can never get to fluorine before bromine. It is rather hiding behind this carbon. It means that the movement counterclockwise, we do not get to fluorine before bromine. Please, that this explanation sits well with you.
There again.
Hello.
Yeah.
Say,
Hi. Yeah, please.
It's clear. Whatever I've just said is clear. What again do you want to hear?
say, can there be a case where the fluorine will be at the place of chlorine and then chlorine will be at the imaginary line? Can you have
Yes.
such a case?
Very good. That is very good, question to ask. So, in my case, you know what I've given to you and I'm using to explain. It is so easier because now the least group, that is number 4, I have put it on the imaginary line, the hidden group. So your movement becomes so easy to get. But in an exams, I can give you this same compound where I will bring fluorine here to where the chlorine is, and where the chlorine is to where the fluorine is. In that case, you cannot say that when you are moving, okay, when you are moving, the higher group, which is the chlorine, as against the fluorine, that one should go in hiding. No, you should always see the first 3 priority groups, so that when you are moving from 1 to 2 to 3, the direction you follow will let you get your configuration right as either R or S. So when you have a situation like that, then what you will do is do what we call, you can do an interchange, okay? 1, you can then flip the molecule. When you flip the molecule, then if let's say you bring the fluorine to where the chlorine is. So now I gave you the chlorine here and the fluorine here. So taking the fluorine back to the broken line and bringing the chlorine back, it means that the other 2 groups must also be interchanged. Are you getting it?
Okay.
So that
once
your least group goes into hiding, and then yes. Either than that, what you also do is that if you moving from 1 to 2, and then the 3, which should be chlorine, now it is fluorine, because you are getting to the least group, fluorine, you were going, assume the opposite direction as the configuration. So if you were going, so let me say, let me try and see if I can write. So you see, I have brought the fluorine where the chlorine is. Is that right? So let's assume that fluorine takes the position. And then I try to bring the chlorine here. Now I should go to 3. But the fluorine here is not 3. That one is what? 4. So it means that I'm coming to fluorine, which is the least group, before the chlorine. So the direction I was going was what? Counterclockwise, isn't it? So I will assume the opposite, which will be what? Clockwise. So instead of S, so I see the question you asked, that's the explanation to that. So it is possible that from 1, like let's say this one, from 1, instead of coming to bromine 2, you come and see fluorine here. You come and see fluorine, and then the bromine will rather go to where the fluorine is hidden. But I'm saying that when that situation happens, then from 1, you come to 4 before you come to 3, then we are saying that you were going in a clockwise direction. So it means that the configuration will be the opposite. And that will be what? The counterclockwise, which is what? S. You assume the opposite direction that you were going. Now, again, when a priority cannot be assigned on the basis of the atomic number of the atoms that are directly attached to the stereocenter, then the next set of atoms in the unassigned groups are examined. So now let's look at this one on the screen. You see that this is the chiral carbon here. Now you have oxygen, carbon, carbon, and hydrogen, which are directly attached. So we know oxygen is 16, carbon is 12, hydrogen is 1. In this instance, if you assign 1 to the oxygen, then the 2 carbons here, because they have the same molecular weight, it will be difficult for you to assign which one takes 2 and which one takes 3. Please a minute.
Hello, seniors. You see, like anytime doctor want to explain a sensible point to us, then the network is jamming. I don't know whether it's from my side or everybody is experiencing the same issue.
me, even the question I asked, it was the latter part that I got the explanation. When he started, now my network started behaving.
No, it's not your network. I think it's from the doctor's side. Because anytime I want to hear any better explanation, and then the network is jamming. I think it's from the doctor's side. It's not our side. So if we are all of us are facing the same issue, then let's try and then address it.
Okay, I don't know for the rest. If maybe you can get about
Yes, the same
witnesses,
here.
the
The
same.
same here.
Oh,
Yes, I
okay,
wanted.
okay.
It was when you were withdrawing. When you started
If,
doing the
if it's
network
the
was
same,
some way.
then let's address it to him. Because we need a better explanation. And then anytime we need a better explanation, and then the network is fully down. We have to say it. Say, please, you can go over again because your network is not.
Yo, bro.
If everybody is in, yes, in there. I'm listening. So let's try and then address the issue.
All right, I'm back. So I'll just explain it. So the two carbons labeled with blue, you could see that they have the same molecular weight. So you cannot take a decision as to which one should be of a higher priority. So if that happens, then you move to the other group. So this carbon here has 3 hydrogens, and this carbon here has 2 hydrogens, and it's bonded to a carbon. So it makes the down one here to be heavier than the top. And so that one is assigned 2, then the top one gets 3. Okay, so what we are saying is that if the immediate atoms that are bonded to the chiral center are of the same weight, then consider the other groups that are on them to know which one should be given a higher priority before you do your assignment and then show your direction.
Sir, please a question.
Yes.
Please, can you show the slide you guess? The next slide before you came to this. So concerning the first one, the center carbon is a chiral carbon, right?
Yes.
Okay. So if I am to look out for the different atoms bonded to the carbon, am I considering the carbon or I'm considering the methyl and then the ethyl group for the 2 carbons?
Okay, you are considering meter CH3 and then CH2
Okay.
CH3
Oh, okay, okay,
to make it 4 different groups. That makes this carbon chiral. But when
okay,
you
sir.
are assigning the order of priority, okay, we don't lump them. You don't put OH together and say it's 17, okay, and then
Okay,
you don't put CH2 CH3 together and say it's 29 to say that
okay,
CH2 CH3 29 is heavier than what OH.
okay,
That one you don't lump them up. You only consider the atoms that are directly attached first, and
okay,
where
sir.
they are carbon, then you consider the groups on them.
Okay, thank you.
All right. In an exams, I'm going to give you a number of organic compounds, and then I will tell you to indicate the configuration around the chiral carbon. First of all, I will tell you, check whether they are chiral centers. Put asterisks there on the chiral carbons. And then when you are done, then I'll ask you to indicate the configuration around each chiral carbon. So this is just giving you more examples, okay, where we have OH, CH3, and then the acid group COH. You see that, and then the hydrogen is here, so it's chiral. But then you see, we consider oxygen, carbon, and carbon, and the oxygen was given 1. Now, where we have carbon, carbon, the one with green carbon has 3 hydrogens, but then the carbon here with blue has oxygen. So that makes it heavier than this carbon here. And that's why it was given 2 and this one 3. Of course, the hydrogen is the 4th, the least group. Okay. And then if you look at this, what's the configuration? You see that initially the CH3, which is the number 3, was on the broken line. And then the hydrogen, which is the least group, was on a solid line. So what we do is that you see that you flip, okay, like a steering wheel, so that the least group, okay, goes into hiding, and then the other groups, stays in the plane, so that when you move from 1, you go to 2 and you go to 3, and that is what anti-clockwise S. So that is what is given here, and you can see more examples. Since you have the slide, take your time and look at it. This one is not a rush, okay? You need time to look at it, and then you will be fine. Now look at the properties of enantiomers. I've already explained this one, so I wouldn't want to waste time here. They have identical physical properties such as boiling point, melting point, refractive indices, solubilities, density. They are all similar, okay, except optical rotations. So if you take R2-butanol and S2-butanol, these are a pair of enantiomers. They only differ in terms of their rotation. This one is R and this one is S. Now look at their boiling point, 99.5 degrees, 99.5 degrees, the same. Look at the density, 0.808, 0.808, the same. Look at the refractive index, 1.397, 1.397. So we are saying that when you are given any pair of enantiomers, and you are talking about a comparison between their physical properties, whether it's melting point, boiling point, density, refractive index, they are all the same, solubility. The only difference is, whilst one rotates the plane of polarized light to the right, which is clockwise, R, the other one rotates to the counterclockwise, sinister, which is what, S. And also how they react with what, optically active reagent, is done differently. So all this information is what I have explained earlier on. So there's no need of what, wasting much time here. And we've been talking about optical activity, plane polarized light. I've explained that one. And then the So when you say polarized light, you see that all the arrows are pointing to the same, direction. Okay. So a plain polarized light is a light that has been passed through a nickel prism or other polarizing medium so that all of the vibrations are in the same plane. So this is showing a plain polarized light. And this one is showing what? A non-polarized light. You see, they are moving in a haphazard manner. So when you talk about plain polarized light, that is what it means. Then this is the polarimeter we talk about, an instrument that is used to determine whether a substance is optically active or not. And if it is optically active, it is used to measure the direction and the degree of what? Rotation. So you be able to use this one to measure whether it is R or S. And then the angle of rotation to this polarimeter is used to measure it. Now, you can find this instrument in the chemistry lab and even in the physics lab. The details of its operation is all captured here, which for time factor, please, I will not take you through. And you see the polarizer, you see the plain polarized light here, then the sample cell, and then when there's rotation, and then you can then see it or observe it using the analyzer. Okay. So when you have time, let's look at how the polarimeter, how it operates, the various compartments, and then you will probably appreciate its operation in detail. It's just diagrammatic explanation, and please create time and then look at it later. So in terms of the optical activity and then the rotation, we have talked about the R and then the S. But then wherever you see the R, okay, is the same as the plus. And wherever you see the +2 is the same as what? The D. Okay, there's that the D, the stereorotatory, is the old classification or old form of what? Naming it. And then the new one is the use of the plus or the R. Then when it is counterclockwise, the older form is what? L, that's level rotatory. And then the new form is the use of the minus or the S. So just be very conversant with this, and then you are okay. So you need to be able to know the definitions of these terminologies. So stereorotatory, when the plane of polarized light is rotated in a clockwise direction when viewed through a polarimeter. It is normally denoted by plus or the letter D. Okay. Then level rotatory is when the plane of polarized light is rotated in a counterclockwise direction when viewed through a polarimeter. It's also denoted by minus or L. The angle of rotation of plain polarized light by an optically active substance lectures today. So I wouldn't want to confuse you. I will hold on and we'll end here. In our next meeting, I will take you through some, but you have the slides. So please, on your own, go through them. And then the tutorial questions or the review questions I will give has a number of questions which you have to apply this equation to solving them. And then we will go through that and then we will get to the latter part. This course is not voluminous. And for that matter, it's just understanding these key thematic areas, and then you should be okay. So we'll end today's class so that you take some rest, and then we'll meet again.
Hello.
Bye for now.
Hello.
Yes.
Oh, Doc, please. Oh, my network had a problem, so I just rejoined. Oh.
Yes. So it's being
For about
recorded.
10
So
minutes.
try and get the recorded lectures. Okay. for network issues, you are not the only person with that challenge. I've even seen that you keep on dropping and joining plenty. So
Okay.
try and get the recorded lecture, please. It will really help you.
Okay, thanks.
All
Then
right. So please, yeah, we'll end here. And then please, the course remind me of the tutorial questions and then the review questions so that I can share them with you. It's very, very important.